Okay, today we're going to talk about multipliers. So first, let's look at an example of a multiplier in digital logic. All right, so here I'm going to multiply the numbers 12, represented as a binary number, times 5. Now the top number is called the multiplicand and the bottom number is called the multiplier. Now we're going to do the multiplication operation by forming partial products. So for instance, the first partial product, I'm going to multiply 12, 1, 1, 0, 0 by 1, the least significant bit of the multiplier. And for the next one, I'm going to create another partial product using the next significant bit with a shift operation. And I'm going to keep doing that until I've formed all of my partial products. And now I'm going to sum all of my partial products using adders. All right, and now if this is all done correctly, I should have an answer of 60. I know that 12 times 5 is 60, and indeed I have 4 plus 8 plus 16 plus 32 does indeed equal to 60. We call this the product. All right, so I can determine my basic multiplication operation. So here I have a truth table. Of course, if either the multiplicand or the multiplier are 0, the product is 0. And I only get a 1 if both the multiplier and the multiplicand are 1. And we can recognize what this function is. This is an AND. All right, so we are going to form our partial products by ANDing the multiplicand and the multiplier. And if we do this, the product is going to have m plus n bits, and it's going to have a range of 0 to 2 to the n minus 1 times 0 to 2 to the m minus 1. We can expand this out to say that the range is from 0 to 2 to the n plus m minus 2 to the n minus 2 to the m minus 2. All right, we can also formally define the operation that we're doing. So our multiplication operation, the product of m times n, can be defined as the sum from k equals 0 to m plus n minus 1 of p of k times 2 to the k. So we can break this down and say that this is equal to the product of two different multiplications, the sum from I equals 0 to m minus 1 of m to the I of m sub I times 2 to the I times the sum from j equals 0 to n minus 1 of n sub j times 2 to the j. And then we can simplify this as a nested sum where we're forming partial products. And then in the outer loop, we're summing them. Okay, so next let's look at how we make a multiplier. And the first multiplier we're going to look at is to do a basic shift and add, and this will make a serial multiplier. All right, so I'm going to draw a block diagram. All right, so here's my multiplier. I have a multiplicand that's feeding into a 32-bit multiplicand that's feeding into a 32-bit adder. The adder outputs into a shift register, and there's control logic. Now, how does the control logic work? Well, first we're going to initialize the m plus n bit shift register at the bottom, with the lower 32 bits being equal to n and the upper 32 bits being equal to 0. And then, depending upon what the 0th bit is, we're going to do an operation. All right, so if the LSB is 0, then we're going to do a shift right. But if the LSB is 1, we're going to add and then write to the register. And we're going to keep doing this until we've gone through the entire multiplier of 32 bits. So we can ask about how this how this multiplier compares. So it's very slow. It takes n cycles, where n is the number of bits in the multiplier. It is small. It only has one adder, a register, and some control logic. And so when we're using an adder like this, we're basically trading off size for speed. All right, so our strategy going forward, if we want to make a faster adder, is we're going to try and trade off size for speed. And we're going to do that, 1, by using parallel adders, or 2, by trying to compress the partial products, or 3, by trying not to generate partial products at all. All right, so that leads to maybe the simplest of these classifications of adders. We're going to call this an array multiplier. And essentially, we're going to use tiled adders to form partial products. And I'll draw the block diagram. Okay, so let's say that we're trying to multiply two numbers, x and y. So we have the multiplicand as y and the multiplier as x. And you can see what we're going to do is form partial products. So the first one we're going to do is form the partial product for x0 times the multiplicand. And then we're going to do the same thing for x1 times the multiplicand. And we're going to do a summation. So this is just the first row. Now we can save area by only using half adders instead of full adders, where we don't have have 3 inputs coming into the adder. So the way that this will work is we'll shift the results of these additions. So you can see that the MSB in this particular case only has 2 inputs, so we can use a half adder. The next bit down needs a full adder. We need a full adder here. And we don't have a carry in into the first row, so we only have 2 inputs, so we can use a half adder. Now I'm going to fill out the rest of the array structure, but we have to form the rest of the partial products and sum those as well. All right, so here you can see the rest of the array created. Basically, we've used redundancy in order to create all of our partial products. We've saved a little bit of area by only using full adders when absolutely necessary. Now let's look at what our critical path is. So our critical path starts at this half adder. We have to go through a full adder, through another full adder, through this half adder, down through a full adder, over through a full adder, down through a full adder, and then finally over through a full adder. And so you can see that the critical path has 7 full adders in its delay chain. Now I'll note, if you look at the structure, you can also find a few different cases where you have a critical path of 7 full adders. Now we have another problem. When we create partial products, we're going to create the number of partial products is the same as the number of multipliers, of number of bits of the multiplier. And so when we add those, it's the same as adding multiple numbers. Okay, so let's assume that we're going to add the following partial products: 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, or 0, 0, 1, 0. In other words, 1, 7, 13, and 2. Now the first operation is to add 1 to 7. So we know that we should get 8, or 1, 0, 0, 0. And indeed, if we add those two numbers together, we would get that. Now we need to add 8 to 13. And here we should get 1, 0, 1, 0, 1 to equal 21. But if we only have 4-bit adders, we have overflow. So we have the wrong partial product. Now we're going to, again, add the next 2 bits. We should get a total of 23, or 1, 0, 1, 1, 1. But again, we don't have the number of bits to represent that, so we have an overflow bit. One way that we can fix this overflow problem, where we're going to get a wrong answer when we sum our partial products, is to try and use some carry save adders. So our carry save adder saves the carry, and then this can be added to the sum to produce the proper result. So if we want to put this all together, let's look at what an architecture looks like adding partial products with a carry save adder. Okay, so again, we're going to try and add the same numbers, 1, 7, and 13. And if we do this, we should get a sum that's equal to 1, 0, 1, 1, and a carry that's equal to 0, 1, 0, 1 coming out of the first stage. We're going to now go into the second stage. So I'm going to add 0, 1, 0, 1, 1, 0, 1, 1. In other words, the carry and sum from the first stage to the partial product going into the second stage. And I apologize, I need to shift the carry. There we go. And now I'm going to add these. And I'm going to get another sum and another carry. So those are going to be going into the third stage, 0, 1, 0, 1, 0, and 0, 0, 0, 1, 1. And then, of course, I add these two together, and I get 1, 1, 1, 0, 1, 0. This is the sum. And remember, the sum should have equaled 23, and indeed, this does equal 23, so this gets this correct. So now let's look at how we build a multiplier out of this. Okay, so here I have an array just like before. And I've formed partial products, and I'm going to add them. So everywhere where I have an arrow going to the top of one of these adders is it represents a partial product being added into one of the, or being input into one of the adders. All right, so here you can see our multiplier array. Each of these outputs is producing a bit for the product. Here you can see that what we're doing is we're shifting the carry before adding. And just like before, anywhere that we only have two inputs, we can use a half adder. So I'm just going to mark the half adders. Everything else is a full adder. Okay. Now, these additions need to be very fast, so we can use things like dominoes. In order to get our product quickly. And our critical path starts here and goes along the product path all the way to the output. Now, one thing about the multipliers, we've drawn these arrays as being diagonals, but this isn't very area efficient, so we would probably draw this more as a rectangle if we were doing this in reality. All right, so here's our rectangle, and then we would draw our inputs and have them flow in the correct manner, like follows. So here are our carry save adders. We have the carry propagating to sum into the next stage, and the sum propagating forward into the next stage as well, just going one bit down. And we can keep doing this basic structure. All right, so there's a more efficient floor plan for our carry select adder based multiplier. Okay, now one thing that we also have to consider is that this is for unsigned multiplication, but we also might have to do signed multiplication, and so we do have to consider using 2's complement for that. And one thing that we haven't done thus far is to try and simplify things, and there are many different methods to simplify them. So for instance, one method is Booth encoding, where we're going to try and compress the partial product tree to not have to produce as many partial products. Okay, so let's consider that we have a number like the following. So here in this position, this is multiplied by 2 to the 2. In this position, this is multiplied by 2 to the 7. And what we have here is bits 2 through 6 are 1s. Everything else is a 0. And so if we were to sum this, it would be 2 to the 2 plus 2 to the 3 plus 2 to the 4 plus 2 to the 5 plus 2 to the 6. But we can also notice that this is equal to 2 to the 7 minus 2 to the 2. So in general, if we have sequences where we have strings of 1s and that are followed by 0s, we can write those in a special way. So let's say we have this 0 in the qth position, so this is 2 to the q, and we have our last 1 over here in the rth position, 2 to the r. So we can write this as 2 to the r plus 2 to the r plus 1 plus everything up to 2 to the q minus 1 is equal to 2 to the q minus 2 to the r. So if a multiplier has a string of 1s, we only need to perform an addition, shift, or subtraction in shift. And so that leads us to the Booth method or the radix 2 method. And what we're going to do is look at the current and previous bit of a multiplier. So here we're looking at the current bit I and the previous bit I minus 1. And depending upon the combination of the two bits, we're going to do the following things. If it's 0, 0, we're going to shift with no addition. If the current bit is 0 and the previous bit was 1, we're going to add the multiplicand. This indicates that we have an end of a string of 1s. If the current bit is 1 and the previous bit is 0, we're going to subtract the multiplicand. This indicates that we're at the beginning of a string of 1s. And if the current bit is 1 and the previous bit was 1, we're just going to do a shift with no addition or subtraction. All right, so let's look at an example. Okay, so we're going to assume that we're adding 110 or multiplying 110111 by 110011. And in the case of the multiplier, we're going to assume that all of the zeros before the LSB, or all the numbers before the LSB, were zeros. And so we're just going to compare 2 bit positions. So here we have a 1 0. This would mean a subtract. Then we have a 1 1. This is a shift. Then we have a 0 1. This is an add. Then we have a 0 0, which is a shift. And we keep doing this throughout the entire number. Another way of looking at this is what we're really doing is recoding x. So whereas before x was equal to 0, 1, 0, 1, pardon me, x was equal to 1, 1, 0, 0, 1, 1, we're going to Okay, so let's then think about what our worst case scenario is. What if x were equal to 0, 1, 0, 1, 0, 1, 0? I think I added an extra bit here. So what if x were equal to this? We have just an alternating sequence of zeros and ones. In this particular case, of course, we're not going to get as much savings because as we compare our 2 bits, we're always going to end up doing a subtraction or an addition based upon our rules that we had before. All right, so we're not going to save too many operations in that particular case. But in general, we can show that the radix 2r method, or the Booth method, yields n divided by r partial products. Okay, so we're going to stop there for this lecture, but I will note that there are many different things that we can do. So for instance, in this particular case, we only looked at 2 bits. What if we were to look at more than 2 bits? We could look at 3 bits or 4 bits and try and come up with an encoding scheme to reduce the number of partial products in that particular way. And that's the general strategy for trying to reduce the complexity of multipliers, or at least one general strategy for trying to reduce the complexity of multipliers. Okay, so we'll stop there, and I'll see you next class.